Hi everyone. So this is lecture 16. This is on tips for solving engineering problems. So these are my tips for you for solving algebraic problems that are either linear or nonlinear problems when they've got units, when they're a story problem, basically, when it's not just a math problem. Okay? So the outline today, I have 4 tips for you. The 4 tips are outlined here, so they're going to be identify the kind of problem and set up your method, write it in standard form, take care of the units, okay, and then make smart guesses, right? So let's go ahead and dive right in. So let's start with a little background. Why do you need some tips for these? So engineering problems are usually harder for most students than what I call pure math problems. So we'll see some examples today of some engineering problems, but maybe a pure math problem might be, x squared plus 4x minus 2 equals 0. It's just some quadratic equation. But usually, if you have something that's got engineering units, it's a story problem, that seems to be a little bit harder. And what's going on underneath the hood here is that the math is exactly the same. You're going to have either an algebraic problem, a linear algebra problem or a nonlinear algebra problem. But there's sort of a different window dressing on top of that, all right? And that different window dressing, sort of can confuse you or make you not see the connection between that engineering problem and then the methods that we've been using. So today we're going to practice a little bit of that. I'm going to give you my tips for how to go about turning those engineering problems into math problems and seeing the connections there. All right, so it's easiest to illustrate this by using an example problem. So I'm going to use this example problem right here that I'm going to explain here in just a second to go through the 4 tips. I could just tell them to you, but it makes a lot more sense if I show how I'm going to go ahead and do this on this. So this is an example from a fluid mechanics class, so a chemical engineering fluid mechanics class. And so I'm going to read the problem and then we're going to talk about it a little bit. So the problem is, what is the diameter of a 100-meter pipe where the supplied head is 32 meters and the flow rate is 6 liters per second? All right, so if you haven't had a fluid mechanics class, I don't expect you to know that. All right, and as a matter of fact, it might be even a little bit easier to solve this problem, okay, given that I'm going to give you all the equations once you see, what those equations are, okay, how to do that. But the basic idea here is that I have a pipe that's flowing. It's 100 meters long, so it's a very long pipe. And I'm giving it a certain amount of energy or a certain amount of pressure to push the fluid through. And it turns out you can write that pressure in a length unit in what's called head instead of a pressure unit. And it's basically take pressure and divide by gravitational constant times the density, so pressure over rho g. In this case, so that gives you 32 meters. And one way to think about that is it's how much, if you took a sort of amount of this fluid and you had to raise it up, you could have that potential energy to raise it up 32 meters, okay? And then the flow rate is 6 liters per second. So, that's a pretty good clip of a flow rate, all right? And you can assume this is water. So water has a viscosity of 1 centipoise, and it has a density of about 1,000 kilograms per meter cubed. All right? And so let's look at the equations that we'll learn in a fluid mechanics class to solve that. Here, there are 4 equations here that we're going to use. So the first one here is this relationship between the head, h, and then these other guys over here. And essentially, this is telling you the amount of energy or head that you need, or that you're going to lose rather, when you're flowing in a pipe of a certain distance L. So here's this distance L. You're flowing at a rate of velocity v, and you've got, this what's called a friction factor here, okay? So this, I'll just write down, this is the head, this is the velocity, okay? This is the friction factor, okay? This is the pipe diameter, okay? And this is the length of the pipe. Okay, so we've seen some of these already, but some of them we haven't seen yet. And this one here, the pipe diameter, that's what we're trying to find. Okay, the next thing here is there's this relationship between the friction factor F and this RE here, which is the Reynolds number, which we get out. And the next one, all right, this is basically a relationship between the fluid velocity, how fast the fluid is flowing, and some other stuff kind of built into that, and how much energy we're losing. Okay, this friction factor tells us how much energy we're going to lose. All right, so if this is bigger, it's worse. All right, and there's this relationship here. Okay, notice that the friction factor is on both sides, so this is an implicit equation. So we can't just write down an answer for F, say, and plug this in and rearrange on solve. Okay. The next one here is the Reynolds number. One way to think about the Reynolds number is as a dimensionless velocity. So it's a velocity where we've divided by some other units. Okay, so it doesn't have any units on it, and it's this quantity rho v d over mu. And then the last part is how do we get the velocity from the flow rate? Well, if I have a pipe and it has a certain flow rate, which is volume per time, if I divide by the area, I get an average velocity of that fluid, and so we can get that average velocity here. Okay. So this is our example problem. So let's go ahead and start then on our tips. We'll refer back to this guy when we need, and I would maybe put a box around it, but I'm worried about my drawing skills. So maybe I'll just put a blue little band here, and we'll call this one 1, this one 2, this one 3, and this one 4, just so we can remember those equations if we need. Okay, so let's get into the tips. So let's put this right here. Let me scroll. Oh, I need a new page. What are my tips? Okay, tip 1, all right. Tip 1 is identify the types of equations. Okay, and pick a method. Pick a solution method. Okay, so that's tip 1 to solving these kind of problems. All right, so when I say identify the types of equations, what do I mean? I mean, is it linear? Okay, or is it nonlinear? All right, we're dealing with algebraic problems here, right? So you want to identify the kind of math problem. Is this a linear equation or a nonlinear equation? What numerical tool do I need? Okay, so if it's linear, right, and I'm going to do, am I going to do this in regardless, I'm going to say, is this going to be in Excel? Is this going to be in Python? Which is the best tool to use, right? Which one is, or is it by hand? Okay, obviously we're not doing by hand in this class. This is a computational tools class, but that's the whole idea, right? Okay, and then once I've identified this, right, am I going to use numpy.linalg.solve? Okay, when is that one useful? How does that one apply? What about, scipy.optimize.root? Okay, these are the different different numerical tools, say, inside Python that I might use. Excel, I might be thinking about solver, right? Something else I might be doing in here, okay? So let's think about our example up here in this context. Let's look at what this is. All right, so the first thing we should see is that we almost certainly have a nonlinear equation because we have, f here and f here, right? So we have two, this implicit term, and there's a log, and so we almost certainly have a nonlinear equation, right? Now, you might be a little bit careful because you say, well, how am I going to get f? All right, up here, I need f up here to find d. So I'm going to, somehow I need to solve for d here, okay? But, because f is inside there, we're almost certainly going to have to do a nonlinear equation. There could be a case where this might be a linear system if we already knew f, and say we already knew v squared and we knew d squared, and there was, if the knowns and the unknowns were different, okay? So that's really where we're going to get to in the next tip is to pay attention to what your knowns and unknowns are, all right? But if we stare at this guy for a few minutes, it's almost certain that we've got something nonlinear, all right? And so our example, I'm going to put that down. Our example, okay, we have a nonlinear system, all right? And so we should be then expecting to use something like Python's scipy.optimize.root, okay? So I'm going to put that down, scipy.optimize.root, okay, which is in Python, all right? So already we looked at the problem, and by identifying the types of equations, we already know where to go, right? And on a test, that's worth a lot, right? That's usually worth a bunch of points right there, just being able to identify the problem. So don't get hung up at the beginning, right, on, oh my goodness, this is some hairy equation, right? Pick that out, analyze that. Pick, is this linear or nonlinear system, and what am I going to use to go forward there? Okay, tip 2. Which is convert to standard form. Convert to standard form, okay, or vector notation, which we'll see is key to this. Okay, so the key to converting to standard form, all right, is being able to identify your knowns and unknowns. Okay, other than this, other than identifying knowns and unknowns, it's the exact same process as in your math problems, okay? So otherwise, same process as math, okay, as a pure math problem. Okay, so let's see how to do that. Let's see what that means. So I come up here and I have a bunch of variables. So let me write down the different variables that I have and see and put them in a known or unknown category, right? So let me make a thing here of knowns, okay, and unknowns. Okay, and maybe you have to scroll, which is maybe less than ideal, but let's just look here for a minute. Okay, so in the problem here it says we have what is the diameter? Okay, so the diameter d is definitely going to be an unknown. That's the thing we care about in the end. All right, we know the length of the pipe, so that's a known, and we know the supplied head h, that's a known, and we know the flow rate q. Okay, maybe I didn't identify that one down there, but that's the flow rate. Maybe you picked up on that. Okay, so let's see some knowns that we had. Then we had the flow rate q, we had the length l, we had an unknown was d. All right, let's see, what else did I say? Flow rate, the head h. Okay, we also know the viscosity and the density. Okay, so we know the head h, the viscosity, the density. All right, we're doing pretty good. We don't know these guys over here. Look at these 3 things. We don't know the friction factor, we don't know the Reynolds number, and we don't know the velocity. Okay, so I don't know the velocity, I don't know the Reynolds number, I don't know the friction factor. And let me see, so is that all of them? H, L, Q, rho, U, and there's one more thing up here, if you know. Notice we need to know somewhere right there, we need to know the gravitational constant. Okay, but we know the gravitational constant, we're on planet Earth, so we know G. All right, so now all these knowns, these are going to be quantities that are just going to get plugged into our equations up here. All right, so what we want to now do is convert these unknowns into vector notation. So these ones we're going to convert to vector notation. Okay, and so what we're going to do is rewrite the equations that we had above, right? And we're going to say, make these guys different variables in our vector notation. So to be consistent with my notes, I'm going to call this one x0. The Reynolds number I'm going to call x1. The friction factor I'm going to call x2. And then the diameter I'm going to call x3. So sorry that's not in order, but this will help me be able to double check my notes so I don't make a mistake later on. All right. And so at the end, I can now write x vector, right, which is going to be x0, x1, x2, x3. Those are my unknowns. And that's now going to be v, Reynolds number, friction factor, and diameter. So those are the things I don't know, right? And, now we're going to want to write this in a standard form. Okay, so remember standard form is either for a linear equation is ax equals b, right? That's for linear system. For nonlinear system, I have f of x, where both of these f and x are vectors, is equal to 0, nonlinear. And you recall that in both cases, when I go to code them, I need to use a vector at some point, right, to put them in, either to, in the Python root function, right, or, if I'm calling a linear system, I obviously need to have a vector there for x, okay, and so I need to be able to write these in standard form. So what I'm going to do is go back and convert these equations up here that I've written down, and I want to write them so that I plug in, this substitute in this vector notation in for these equations here. All right, so I'm going to scroll down and I'm going to write that out. I can't flip back and forth because I think I'm just going to lose you to do that. But let me write down, so my first equation, which I'm going to call f0, which is going to be equal to 0, is going to be h plus x0 squared divided by 2g multiplied by 4l x2 divided by x3 close brace. All right, so let's come and look at that. Maybe I can even just lasso these real quick. Maybe that'll allow me to, I'm going to get a little bit bigger of a lasso. Maybe this will help us out. I'm going to copy, I'm going to paste them down here. Pull them over there. Well, let me turn them, let me turn them a color. Let me turn them that color so we can reference. All right, so let's see, there's an arrow right there, an arrow right there, and a piece of an arrow right there. Okay, so just cleaning these up a little bit, sorry about that. All right, so look at this. I had a minus v squared right there, all right? So this v is x0 right there. 4lf, f was x2, d was x3, all right? But all the other pieces in here at the end, should just be knowns, right? So h is a known right there, l is a known right there, okay, g is a known right there, all right? And notice that I did the standard notation. I brought, this over here. It doesn't matter either way. It can multiply by -1. And so that I set this equation equal to 0, okay? So my f0, right, is this one. But that's only f0. Now I need to do f1. So let me write f1 down. f1 equals 0. And let me copy this guy over, right? So now I'm going to move this one over to that side, or vice versa. So I'll have 1 over the square root, and f up here is x2 plus 4 log 10. The Reynolds number is x1, so this will be x1, x2 minus 0.4. All right? And so notice now, as I'm doing this, by the way, that I can tell really easily now which is a linear and a nonlinear system as I'm trying to write this down, right? I've got x0 squared. If I end up with a linear system, I would only have something that has, say, x0s and x1s all added up, right? In our linear format of a constant times a number, constant times a variable, constant times a variable, etc. Okay, so it's really clear now that this is a nonlinear system, right? So if you thought you had a nonlinear system, all right, and you get to this stage and you start to write it down equals 0, you'll notice that you can rewrite it in an ax equals b notation, all right, and then you can go back and rethink your strategy. So it's sort of a good point to check that, all right? F2 here is this Reynolds number equation, so the Reynolds number I call x1, so x1 minus, and then I have rho v is just off my screen up here to the top, which is x0, so this will be x0. D is x3, okay, and divided by mu. Right? So again, right there, I've got that piece, right? F3 is my last one, equals 0. Now I've got the velocity, which I said was x0, right, up there. So x0 minus, and then I have 4q. Q is a known. Remember, that's the flow rate. That's what my first known I set up there. And then pi, and then d is x3 squared. Okay, so now those are my 4 equations. Okay, so again, this should use, all right, so maybe make this comment down here. All right, so this should use all of x0, x1, x2, x3. Okay, it should use all of them, and only the knowns should be left. Okay, should use all of these, and I should get rid of all unknowns. All right, so that's tip 2 or step 2, is to convert this into standard form and to make sure I've identified all my knowns and unknowns. All right, step 3, tip 3, okay, is convert to consistent units. Okay, so we talked about this way back at the beginning of class. If you've seen my or if you've seen the other lectures here, okay. So we did this. Oh, I keep hitting that. We did this at the beginning of class. So this isn't really new, all right, but it's important. So not new, but it's important. Right? You just to remind us of what you do here. All right, you pick either SI or imperial units, either one. All right. So in SI, recall you're doing kilograms, meters, and seconds. And in imperial units, you're picking feet. I guess I should put the mass. I say you should pick slugs, feet, and seconds. All right. And in most mechanics problems, okay, and I guess if you have to pick a temperature unit, you can have a Kelvin over here, and over here you can have a degree Rankine. All right. And notice that these Rankine, these are absolute temperatures, right? So for pretty much all problems in chemical engineering, you can convert them into these units, right? You can have, you've got a mass, a length, a time, and a temperature degree, all right? And over here, you've got mass, length, time, temperature, degree. If you put it in these units, all right, they'll all come out, your calculations will all come out in these same units, and your life will be a lot easier. You won't have to spend a lot of time converting units in the middle of your calculation and getting lost, all right? So as an alternate, okay, or what I might call an advanced technique, okay, if I can spell technique, would be to make it dimensionless. And the reason I throw this one in there is because as you go on in your engineering career, you're going to learn about dimensionless numbers like the Reynolds number and the friction factor. I mean, if you ever revisit this, I want you to think, maybe I should make it dimensionless. That might be easier. When I do numerical calculations, we almost always make our calculations dimensionless. They allow us to pick certain scales that we care about, and allows you to reduce the number of variables that you need in the problem, and that sort of helps you out quite a bit. My advice would be to make it dimensionless in the advanced technique, but for this class, and for many cases, it's actually good enough to just pick standard units. In a way, you're sort of making it dimensionless in these units. If that's not really, anyway, I don't know if that confuses you or not, but that's one way to think about it. Okay, so let's look at our example here, and think about this. Maybe that's actually a little. I want to rephrase what I said earlier. It's not when you pick these standard units, you're not making it dimensionless. When you're making it dimensionless, you're actually picking units that are sort of the natural scales of the problem. So it's actually something where you're picking units. In the case of dimensionless, it's a different way of thinking about units. All right. So in our example, we've got Q, which we said was 6 liters per second. So let's convert that to meters cubed per second. Well, that is a pretty easy conversion. I know off the top of my head, it's just a factor of 1,000 to meters cubed per second, right? So now I'm in meters and seconds. If I have, and I guess what I've done here is I've picked SI, right? SI are often the easiest, and in this case, my problem statement gave me things in meters and liters, all right, and centipoise and whatnot. So SI units were the easy one to convert to. If you're given something in feet, stick with feet. Often that's what the problem is asking for at the end. So that's what you should really do the problem in. All right. So the viscosity is 1 centipoise, which should be equal to 10 to the minus 2 kilograms per meter second. All right. Again, centipoise is something, if you've taken fluids, you know what it is. It's a unit of viscosity. If you haven't, you can just take my word for it. The height, the head, we're told, was minus 32 meters. That's already in the right units. The length is 100 meters. That's already in the right units. G is in 9.8 meters per second squared. And rho, we said, was about 1,000 kilograms per meter cubed. Okay, so notice all I have here, right, are meters, kilograms, and seconds. That's all I have. And notice now, too, that now that I've identified my unknowns and knowns, I only need to convert the knowns, right? So these are the knowns. Okay, and now I can anticipate what unit the unknowns are going to be in, right? So if I come up here and look, I can guess what the unknowns units are going to be. So if I say what were my unknowns, I haven't calculated them yet, right? But I had, let's see, velocity, Reynolds number, friction factor, and diameter. And velocity I know is going to come out in meters per second. Reynolds number I said was unitless. Friction factor is also unitless. And the diameter is going to come out in meters. All right, so I didn't have to do this. This is just going to come out because I'm sticking with these units. I don't even have to think about it or do the calculation. If I wanted to, I could come back up to this, up to my equation all the way up here and calculate what the velocity is, given this is meters cubed per second, and this is in meters squared, and that's going to tell me that's meters per second. And I can go through and double check and make sure all that's good. But the nice thing about once I convert this is now I'm ready to plug them in the units that they go in as, and off we go. Okay? All right. So then the last thing here will be tip 4, which is make smart guesses. Okay? So this is really for nonlinear systems only. Okay? Or at least for, I guess maybe nonlinear systems and very big linear systems. Okay? And for the purposes of this class, we've only used what are called direct methods to solve linear systems. So we've used Gauss elimination. We haven't used iterative methods that, for large sparse matrices. Okay, so for this class, you don't need to do this. Okay, not for this class on these really big linear systems. Okay, with iterative methods. But for a nonlinear system, right, we use these iterative methods, and you have to have a guess. And I often get lots of questions from students that say, how do I come up with a good guess, right? I try to guess, it doesn't converge. I try to guess, it doesn't converge, okay? So I'm going to say a couple things about this. So the very first thing I'm going to say is there are no guarantees. Okay, we're going to start off with the pessimistic point, all right? There are no guarantees, all right? This is one of the things that makes nonlinear equations hard to solve. Sometimes they're just hard. Sometimes you have to have a guess that's just really close. That's a real bummer. So, that's just kind of the way it goes. So recognize that if you're solving a nonlinear system, convergence might be hard, okay? So maybe I'll write that down. Convergence could be hard, all right? But that's not a tip for obtaining a guess. That's just sort of a warning, okay, at the beginning. So the first thing I'll say as a good guess is use some physical intuition. You're an engineer after all, or an engineer in training. It's a good idea to start developing your physical intuition. So let's think about this problem, right? We're asked for something that's got, velocities or flow rates around 6 liters per second. It's water. Heights are, a couple dozen meters. It doesn't make sense that the diameter is going to be the size of the space station, right? Or the size of the Earth, okay? So in our case, right, we might expect diameters, maybe they're going to be on the centimeter scale. Maybe they're going to be on the meter scale, okay? But they're definitely not going to be on the kilometer scale. They're definitely not going to be right on the, light year scale, right? They're not going to be on the micron scale. So if you get out an answer that's, that's on that scale, you know it's going to be wrong. So don't put in a guess that you think is going to be on that scale, right? So the first thing is, use some physical intuition there, all right? The second sort of related point are use the units as a guide. Okay, so if something was given to you, in units of centimeters, centimeters is probably a pretty good thing. There might be hundreds of them, or there might be tenths of a centimeter, but centimeters is probably good. So if we're, like we just went through this whole thing of eliminating the units, right? The original units that were given us in centipoise, and we turned them into kilograms meters per second. Oh, I should have had a -2. So in that case, right, we've lost some information, right? The natural units, okay? So these are like the natural units of the problem. All right, and so if you think about that, again, that's sort of the same idea as use some physical intuition. So think about what are the natural units that you would express a diameter in. It might be in inches or centimeters, right? So again, that's a way to think about that. Another thought for getting good guesses is use a consistent guess. Okay, so for instance, in this problem, right, we have this x vector, and now I'm not remembering what order it's in, but we had something like the velocity, the Reynolds number, the friction factor, and the diameter. Okay? And you could guess a diameter. So suppose you guessed the diameter was like 5 centimeters. Suppose that was your guess for the diameter. Well, if you look back up at these equations up here, all right, notice that the diameter comes in here, but that's the only unknown for the velocity. And then, so you could calculate the velocity. Then once you have the velocity, you could calculate the Reynolds number. Once you have the Reynolds number, you could calculate the friction factor. All right, once you have the friction factor, you could calculate that. Now, they might not all be consistent, but one guess could give you a guess for the velocity, the Reynolds number, and the friction factor, right? So if you can do that, so this is like, maybe to use a bad Lord of the Rings quote, like one guess to rule them all. Okay? So, if I use one guess here, I can use D to get the velocity, to get the Reynolds number, to get the friction factor, okay? They're now consistent with each other. And so the background solution has to do less work to sort of make sure everything else is agreeing, right? It's also easier for you. You don't have to come up with a new velocity guess, right? If you guessed a diameter and you guessed a velocity, and they're not consistent with each other, now that's introducing error already, right? And you had to come up with a guess for this. Okay, so if you can, come up with one guess. Maybe you have to come up with two. Maybe it's kind of a pain to come up with, to come up with a guess for the friction factor because you have to solve it here. So you might come up with a guess for D, which would give you all these, and then you might guess a number for the friction factor. Okay, but this can be especially useful if you don't know a scale for one of the problems. Okay, so this is really good in that instance. So if I don't, have a good scale. Right? Guess a different variable. Right? So maybe if you didn't know, you had no idea what the diameter would be, but you had a pretty good idea about the Reynolds number. Say you know that the Reynolds number is going to be 10 to the 5. I don't know why you might know that, but that's just a silly example. You could use that and then solve for the velocity and then solve for the diameter. Okay? So you play around with those a little bit for. Okay? The next one is if it's 1D or 2D, make a plot. Okay, so sometimes, if you've got something simple, what you're essentially doing here, say I have, the head versus the diameter, and I said, this is equal to 32 meters. Oops, not 22. This is going to be 32 meters, all right? And that's what I said was incoming, and then on the other side, I had this other piece, okay? And that was my, h is equal to minus v squared over 2g for L f over d equation, right? Okay, so suppose I plug this in, right? And I just guess a bunch of d's, guess a lot, guess a whole range of them, right? D maybe goes from, 1 to 100 centimeters. Now I didn't have to come up with a good guess at all. I just guessed a bunch of them, and then I look where it crosses. Oops. It crosses right there. So maybe that one's at, that looks like it's around 6 centimeters, okay? So if you make a plot, that's a great way to come up with a guess. If it's, low enough dimensions that you can go ahead and do that. And notice that in this problem, it might look like, we have a 4-dimensional problem. But again, if I guess D, I get velocity. If I get the velocity and D, I have the Reynolds number, and I can plug that in and get the friction factor. And, maybe all I have to do is solve that friction factor equation a couple times, which is only a 1D problem, and then I can do that and get out my plot, okay? So maybe for more advanced users, you can use a related, okay, but simpler theory. Okay, if simpler is a word, I don't know. I guess this isn't an English class. All right, so suppose I know this. Okay, this is for what's called laminar flow, whereas the friction factor we had above was for turbulent flow. Now, it's wrong, right? This is not the right theory, not correct theory. Okay, but maybe it gives me the right order of magnitude. Okay, so correct order of magnitude, right? Maybe, maybe not, but it gives me some place to start, all right? So it turns out, that this guy is valid for the Reynolds number less than 20, I don't know, depends on what book you look in, 2100, 2300, whereas the other one was good, above that, all right? So suppose our Reynolds number is not that big, this might give us a reasonable number to start with, okay? This comes up a lot. A lot of times you need something like absolute pressure, say when you're solving in thermo problems, and you can use the ideal gas law. Okay, so this would be ideal gas. Okay, again, this isn't the right answer, but it gives you something close. So we've done something like this in my research when we're trying to calculate some phase diagrams. Recently wrote a paper, we had all these ternary phase diagrams. We were calculating ternaries, just 3-component phase diagram. And it was really useful actually to calculate the binary. The binary, which is just 2 components, has some solutions you can just write down by hand. And those gave us some really good initial guesses to be able to start and calculate the thing with the ternary calculation. Okay? All right. So the last thing I'll say is just some basic common sense. Oh, I guess I'm using little dots here. So basic common sense. All right? And so, the velocities, for instance, need to be less than the speed of light, okay? So, this is kind of back to our physical intuition here. Think about if you just had a pure math problem, if I have 3x squared minus 7x plus 2 equals 8, all right? Suppose I had this guy, I would expect my guesses, to be on the order between 1 and 10, right? I wouldn't expect them, plus or minus on both of those guys, right? Absolute value of that. But, I wouldn't expect them to be 10,000, and I wouldn't expect to have anything near the speed of light in a fluids problem, okay? There are other sort of expert intuition things, okay? So it turns out, this is what I'll call expert intuition. Okay, I've done a lot of these fluid mechanics problems before, and the friction factor is always around 1 over 1,000. It might be 5 times 10 to the minus 3. It might be in the Reynolds number, land 10 to the minus 2, something like that. But 10 to the minus 3 is pretty good. Okay, so if you've done these problems a couple times, sometimes these numbers are going to be, about that, right? Or the Reynolds number, for turbulent flow problem is often around 10 to the 5. That's just an expert intuition. That you can use. Oh man, I had a page before. I'm going to add a page after. I was trying to be slick. Okay, that's an expert intuition you can use. Okay, so that's that case. There are other things suppose I have a volume fraction, okay? Right? Physical intuition, right, or just the definition of a volume fraction, right? The volume fraction phi, something like the volume of 1 over the volume of 1 plus the volume of 2, right? And that tells me this is the thing over the total. This tells me that has to be between 0 and 1. I can't have a negative volume fraction. I can't have a fraction of something greater than 1. Okay, so don't make a guess outside those bounds. Or, for instance, I have a pipe diameter. I know it should be greater than 0, right? So again, we're engineers. We're dealing with equations. They're not going to have an imaginary number for a pipe diameter, right? I'm not going to have a negative number for pipe diameter. So use some common sense in guessing positive numbers or numbers between 0 and 1. And this sort of thing can help you out a lot, right? All right. So that's really all I have to tell you about my tips for solving engineering equations. There's a case study. So I'm going to put this down here just sort of as a star. So case study, okay, where I'm going to have another video where you can work through and practice doing that case study to practice doing these engineering problems. All right, it's similar to how the example problems are on the homework, and it's just a good practice example. All right, so I'm going to leave that with you, and I hope that this has been helpful in being able to approach engineering problems when they're not just pure math. And let me just review one more time for you the tips, okay? So we can sort of see what the 4 tips are. So the first tip is identify the kind of problem. Is it a linear or nonlinear equation? What method are you going to use to do it? The second is convert it to standard form, all right? Identify your knowns and unknowns, right? Figure out which your knowns are. Those you'll set aside for the now. The unknowns, make vector format and convert it to the standard form so you can plug it into your computer. The third one is do some units, okay? Make sure you convert all your units to either SI or imperial, whichever they're given in, all right? You plug all your knowns in, convert them all to, say, kilograms, meters, seconds, and Kelvin, all right? Then you don't have to worry about your units so much anymore. And the last one is get good guesses. Use common sense, use alternate theories, use some expert intuition, make a plot, all right? These are some things you can do to go ahead and get good guesses. All right, with that, I'll let you go, and I hope you have a great one.